Chapter 14, Energy Method, Strain Energy in a Rectangular Cantilever Beam. So in this example, we want to determine the strain energy of a rectangular cantilever beam in considering both shearing, the effect of both shearing and normal stresses. So let's see how we can approach this problem. So first, strain energy due to normal for stresses. We do know that a U in strain energy is a half of P times delta from, if you remember, from a P delta graph. Do you remember? We can explain energy in terms of sigma and delta. Mhm. And also we can explain it based on force and delta. So if you define it by force and displacement, it just gives you area under this graph. So that's half of a force times delta, and that is strain energy. Mhm. And at the same time, if you look at the deflection of a cantilever beam, we already know that delta maximum for a such beam, just a cantilever handling a concentrated load at the free end is just PL cubed over 3 times E times I. So if that's the case and we just replace delta here, it just gives us a U, or strain energy is half of P times, in parentheses, PL cubed over 3EI, and that's P squared L cubed over 6EI. That's strain energy due to normal stress, and that's a clear cut. So that's our strain energy due to normal stress. Mhm. At the same time, if we want to calculate the strain energy, because we want to have see the effect of both shearing stress and normal stress. So this time, if you consider the shearing stress, we already know from chapter a if I'm not wrong, chapter 7, which is transverse shear. I can upload that video at the end of this video for you to know. If you calculate a shear in a rectangular cross section, you can easily see that's a 1.5 shear over area. So our shear here is a vertical of P times 1 minus y squared over c squared. So replace V with P over BH. So shear is force over cross-sectional area, which is B times H, and then the rest of the formula. In such case, it just and if you know U, strain energy is just integration of tau squared over 2g times dv. So replace tau xy in this equation and square it. So U tau, strain energy due to shearing stress in that sense, is 1 over 2g times, just take the constant out of the integration, and then integrate it from 0 to L, this part, then dv. And dv is nothing but b dy dx. So if you want to calculate a element of volume, that's a thickness times height times a width. And if that's the case, if you replace this on the main equation, it just gives you, again, take the constant out of the integration, and that's a minus c integration of a 9 p squared over 8 gbh squared, which is the constant Then let's take it out of the integration, the integration of minus c to positive c, and c is just halfway through. So if we just consider it minus c, and that's a positive c. Mhm. Then expand this equation, so that's also squared. Mhm. That's 1 minus 2y squared over c2 plus y squared over c squared dy. Then that's how y is changing. And then dx is just from 0 to L, or 0 to L. That's up to you. Then if you do the math, it just gives you U strain energy due to shearing stress is a, a coefficient 3 times p squared times L over 5g times cross-sectional area, which is this part. Hmm? And total strain energy is just a combination if, or just a U, or U total is equal to U sigma, strain energy due to normal, plus U tau, which is strain energy due to shear. So that's a p squared L cubed over 6EI, which is U sigma, plus the other part, which is U tau. And if you just factor out the U sigma, and then it just goes by 1, then divide this part over U sigma, so that's U tau over U sigma. You can easily reach to this equation, and that's 3EH squared over 10GL L squared. And if you just rewrite it based on U sigma, that gives you U sigma is 1 plus this equation. And we already know from a early chapter in mechanics of material that a shearing rigidity is greater or at least equal to 1/3 of modulus of elasticity. If you replace G by a E over 3, the minimum value of that at least, this part gives you 1 plus zero point 0.9 H over L in parentheses squared. And what that says is very interesting fact, because it just says relative error is less than a zero point 0.9 then times H over L squared. So if the effect of if the effect of shear is neglected, our error is nothing bigger than this value. And if you want to see how that value is negligible or small, if you just consider H over L, if that's is smaller than height of cross section in comparison to the length of the span is smaller than 1/10, which is most of the time the case, then error is something like 0.009 or 0.9%. That's a very small amount. And that's note, that's why in engineering problems, effect of shear is almost neglected in calculation of strain energy. So we just go for U sigma, and U tau is a very small in comparison to, so it says a U sigma is far bigger than U tau in a rectangular cross section, and that's why most of the time we neglect the effect of shear in engineering problem. Thank you. We'll solve more problem in the strain energy method. Thank you.